I hope you don't mind if I close the window a little bit, because despite global warming, it's a bit cold today, but we know that one day it's not representative of the statistics. So I'm sorry, my apologies if I cannot stay today for 1 more hour. And there were several reasons that convinced me that today it would be better just to stick on the timetable. And I'm explaining. So let's look at the timetable, which is missing 4 hours. But on May 16, which is next Thursday, we have the field trip. You have received everything from Serena Ceola and myself. You have the details. And it will be 4 hours actually, and therefore we miss 2 hours only. My proposal is to close the lecture on May 30, which is a Thursday. And I apologize also for this. I anticipated to you that I still would like to make an exam before the official date. Actually, I was invited by the rector not to do that, because you know, the university pushes a lot. I always ignored these requests because I try to do the best for the students, and I think it would be better to dilute your commitments, but actually the rector insisted and said that it's not allowed, we are not allowed to register the exam in a different day with respect to the day when the exam is taken. So I'm sorry for that, but it's something that has legal implications. If I am questioned by somebody that I did that, this is something that is not allowed by law, and it has severe legal implications, and therefore, given that the university had some trouble for this reason recently, so I said, okay, that's fine, so let's stick on the official date, which we already agreed, I think, and it's already on Al-Mezani, if I'm not mistaken. Let me see. I think it's already here in 12 of, no, it's, let me see, no, it's not there. So I need to fix the official date, and let me see if, because I think it is, just 1 second, I'm not sure whether, no, there is no here. Okay, so I think, no, it's not scheduled yet. I'm sorry because I made confusion with the other course. I think June 12 is a month, just 1 second, I check when we can have the exam. I think we could make it on June 10. Let me just check whether I am allowed to do it on June 10, because otherwise it's always the same problem. So, just 1 second, the calendar. It's, yeah, the period finishes on June 7, therefore, let me check. I think we could make it June 10 for sure, but if it is June 7, I'm not sure whether June 7 is allowed. I'm not sure. And because we could make it, okay, is it fine for you, June 10? It's a Monday. It's okay? June 10, it's a Monday for the first exam, and the second would be around, you decide, it could be July 1st. And the third July is something 20, like that, okay? Would it be fine? June 10? Somebody has some problems? Seems not, so 1 second. Oh, let me see, June 10. Oh, actually, June 10 is not possible for me. Let's June 7, it's a Friday. Would it be okay for you? Another exam on the 7th. Let me try whether I am allowed to schedule it on June 7th.
What about the 6th?
Sorry?
The 6th of the June.
I don't think I am allowed. I can try. Just 1 second. Let me check. I can try on June 6. Let me see if it works. I don't think so, but anyway. Okay, let's see. Subscription from today to June 5. Okay, let's see. Okay. No. Let me try June 7. I think June 7 is fine. I can try on June 7. It's okay for you, it's a Friday. Okay? Okay, I hope it works. If not, it's not a problem. Okay, it's already, you can already subscribe, so you can I don't understand why it's yellow. I'm not sure. I would appreciate if you could make an attempt to subscribe to it, because I'm not sure whether you are allowed to, because June 7 is the last day when I couldn't fit the exam, because in principle it's a lecture day. So my feeling is that you may not be allowed to subscribe because it's before the end of your lectures. Actually, it's already after the end of your lectures because we don't have any lecture on Friday, but you know, this is an automatic system. So,
another professor put the exam on 7.
Sorry?
Another professor for another course?
Yeah, I know, but still, you know, he may, he may decide to register the exam on Monday, next Monday, which I could do, but the problem is that I need you to subscribe to the exam in order to to satisfy the requirement of the rector. And maybe that the other professor ignores the requirement of the rector. I cannot, because I was explicitly asked by the rector not to do that, because they know that I am used to do that. If you just can try before the end of this lecture and tell me if you can subscribe, okay? It's already Al-Mizani and you are allowed to subscribe from today. Okay, and then the next one would be after 2-3 weeks. I am willing also to make 2. The only thing that I would like to ask you, because if it is after 2 weeks, it would be June 24, which I think is fine. The alternative may be June 24, July 1st. And if I make June 24, this means that the last one will be, in any case, the last one will be a Monday in July around 20. Could be something like, because I don't want to go after July 20 because some people leave. And it could be July 22nd. So it would be about 1 month from June 24 to July 22nd. If we schedule it on July 1st, of course, it's more equally spaced between June 10, but we can decide June 24, July 1st, or Monday, when we meet, okay? And for now, just tell me before the end of the lecture if you can make an attempt to subscribe, so we are okay. And as I said, I put here May 30 as last lecture day, okay? Good. Now, let me go to our subject today. We have to finish speaking about climate change. We got about here. So, let me make a summary. First, why I'm talking about climate change is already clear, because it is strictly related to sustainability in a quite aggressive way, let's say, meaning that when you design today for water resource systems, you are forced, the institution asks you to take into account climate change. The problem is that we don't know how to do, because, and not only us, but in general, the scientific community, and the technical community in particular, they don't really know how to take into account climate change for climate change adaptation. We spoke about the difference between mitigation and adaptation. For mitigation, the situation is quite clear, meaning that people tend to use models. They are uncertain, sometimes uncertainty is not recognized, but still they are fit for the precise purpose of designing future scenarios for climate mitigation. Meaning that they are not really required to be certain to the level that is required by technical applications. Okay, so they can rely on climate model. They basically rely on climate model for designing future scenarios in order to understand what happens if we don't mitigate CO2 emissions, what happens if we mitigate CO2 emission according to a given percentage, etc. So for mitigation, the situation is quite clear. When we talk about adaptation, the situation is not clear at all. So we don't know how to take into account climate change in the technical design, which is completely different than taking account climate change for mitigation. Because we are allowed more uncertainty for mitigation. In technical design, we are not allowed much uncertainty. So the situation is that really we don't know what to do. And this is the reason why climate change adaptation is not much taught in university courses, because we don't have technical guidelines. The scientific community is working on that. And this is the reason why I wanted to talk about this, because you are forced to take into account climate change. On the other hand, you don't know how to do in technical terms as an engineer. Let me say that climate adaptation is a task of engineers, climate mitigation probably not. It's more a task that is to be dealt with by climate scientists. Adaptation is indeed something for the engineers, but again, we don't have technical guidelines, and therefore I wanted to give you an overview of what we could detect by analyzing the data so far. I mentioned to you that what happened so far is not necessarily representative of what may happen in the future, because there might be tipping points, and this is the main concerns of climate scientists. Some of them are more concerned than others, so there is no really consensus on the possible existence of tipping points. So far, what we could see is that temperature is warmed of an amount that I already illustrated to you. When you talk about other variables, the situation is not so clear. And therefore, I wanted to tell you that for precipitation, which is the driver of water resources, the situation is not really clear. We know that there is natural variability, we know that there is some climate change, but when we look at the data, we don't really see a strong increase of precipitation intensity, precipitation mean levels of precipitation. There are changes which are not uniformly distributed over the Earth. It's difficult to predict these changes because climate models in the simulation of precipitation are much uncertain. Before I move forward, let me make an essential premise. Climate models are not meant, I already mentioned this to you, to support technical design, engineering design. This is not their purpose. They are conceived for studying mitigation strategies, evolution of climate at large scales, but not for predicting meteorology evolution at small scales. So we need indeed to think what we can do, because if we rely on climate models for precipitation, they are not really much helpful. Okay, what about river flows? River flows, we have a similar situation, meaning that sea level, we already talked about it, meaning that what we know is that there is a natural variability of the river flow, which can be summarized, I'm sorry, by this figure, for instance. This is max flows of the Po River, the series that you have, max annual flows from 1920 to 2009, and you see that even in the far past, before global warming started about around 1970, even in the past, we observe a lot of variability in the max flows, and if we try to estimate a regression line in order to understand trends on a window, a moving window that is 50 years long, 50 years is considered to be a quite long extension for statistical analysis of river flows. If we start from 1920 to estimate a trend line between 1920 and 1970, and then we move this line forward, we see that the slope of the regression line is varying. It's blue when it's increasing, it's red when it's decreasing, and in principle you see that even recently, you see that sometimes becomes red. So in principle you can see that there is a natural variability that makes the identification of the effect of climate change difficult. So natural variability, the way we have to analyze it is to use all the series, all the data, under the assumption that what happened in the past is representative of what will happen in the future. And this is the way engineering deals with natural variability, collects data, when necessary integrates data with expert knowledge, and basing on data analysis, we assess variability. This is something that we know how to do. There are classical techniques for doing that. And we are not explicitly talking in this course how to estimate natural variability. We are not talking about classical techniques because we want to focus on sustainability. But just be assured, because I think that in other courses you already dealt with estimation of extremes, extremes means high and low, and there are classical techniques, a lot of textbooks. What we don't know is how to recognize here a signal of climate change and how to take it into account. And indeed, you see that it's not difficult to recognize this signal. And if we look at the low flows, which are more important, because there is a common belief that low flows are decreasing and droughts are intensifying. So let's see what happens for low flows, and in particular for the Po River. I had several discussion with meteorologists and climate scientists, because they say that the drought risk in the Po River has increased. But again, if you make the same experiment, a regression line on the mean flows, mean annual flows, you see that, indeed there has been a big drought in 2003. You may remember it, you were young, but in 2003 there was a very dry summer over most of Europe. It was a very extended drought. Keep in mind that droughts are usually extended. Floods are local effects. Droughts have a meteorological origin, and therefore they are originated over typically ample, wide spatial scales. In 2003 it was particularly large. The drought hit most of Europe. And therefore, after this event, there were concerns that drought may intensify, and therefore there was another, after that there was another year in 2007 with the dry summer. Actually, I think this is 2003 and this is 2007, so there were a couple of years. But then we had, after that, and even in recent years, we didn't have so severe droughts. 2015, the mean flow of the Po River was quite low. But you see that, indeed, it's not easy to detect changes, because you see that also in the 40s we had some very dry summers, as we noticed already. So it's not easy to recognize the signal. And the picture that emerges, it's not really clear. And also for what concerns other droughts that are occurring at the global level, you may have heard about the California drought. It's mentioned there is a link, a Wikipedia link in my web pages on climate change. And also in Australia, they experienced a drought called the Millennium Drought that lasted for 5 years. It started in 2011 and finished around 2015. But actually, it has been demonstrated that this drought were originated by a particularly bad situation in terms of El Niño Southern Oscillation. So it was a cyclical variation of weather rather than an effect of climate change. Again, there are people that are not convinced by this explanation, but what I want to emphasize is that the situation is not really clear. So even the effect on droughts of climate change is not really clear. Still, there is the concern in the institution especially, and in people working in institution, that something bad may happen. I think this is a concern that is motivated because the effect of a drought today, the effect of water scarcity, is much heavier, is much more impacting society with respect to the past, because we have increased the demands, and for water resources are also under pressure for water quality problems, urbanization, increase of sewer discharges, and therefore, indeed, water resource systems today are more stressed than in the past, and therefore it is a reasonable concern. So we are required as engineers to indeed set up strategies for adapting to climate change, which is not bad. I mean, the problem, I think, regardless of what we think about the origin of climate change, man-made or not, it's a very good idea that we try to adapt to this variability. In the past, we didn't care so much. There was more willingness to accept to be flooded once in a while, and people were more prepared to deal with water scarcity because the demands were lower, etc., for many reasons, and also the quality of life is increased. So what I'm saying is that it's a very reasonable concern, and therefore we are asked to, as engineers, to take into account this variability. But of course, there are, when climate change gets into play, then we don't know how to do again. Okay. And therefore, let's talk about climate change adaptation. How can we adapt to climate change? And we have to take into account that we can say climate change with an implication that is human-induced, but let's adopt a more general vision. We want to devise strategies for adapting water resource systems to changes in climate, changes in availability of water resources, which may be man-induced or not. It's not our job to identify if they are man-induced or not. But the tricky question is that we need, first of all, an increased resilience of the system, because we are not willing to accept the same risk that we accepted in the past. And the second issue is that we have to take into account that we may need to assume that something is changed indeed. With respect to using the classical techniques that take the whole bunch of data and make a statistical analysis, we may need to assume that something is changed, because it's a prudential attitude, it is a cautious attitude. And as engineers, we have to take into account, given that there is no certainty about it, and given that it may indeed happen that something is changing, we have to stay on the safe place. On the other hand, we cannot exaggerate in being cautious, because if we exaggerate, the efforts and the resources needed to adapt the system may not be feasible, may not be applicable. Because, of course, the more you stay from the safe side, the more the project costs. And if it costs too much, and again, the more you stay from the safe side, the less the project is sustainable, because you need a huge impact on the environment, huge dams, etc. If I want to store much more water because I want to be safe, excessively safe, I end up with a project that is costly and much impacting. Also, we have to take into account that these interventions are paid with public money. Public money means that society lose competitiveness if it is too much prudent. And losing competitiveness, it means that citizens have to pay more taxes because of a well-known economic implication, market implication. So if we invest public money rather than in supporting industrial development, if we invest public money in climate change mitigation and climate change adaptation, of course, the country loses competitiveness because we don't support economic growth in terms of industrial development. We don't invest in the market, we invest in adaptation. So it requires a forward-looking vision. We lose an immediate benefit because we predict that investing in climate adaptation may produce a benefit in the long term. This is fine, but if we exaggerate, of course, it may become unsustainable for society, for the citizens, because public money means taxation. Today, there is the belief that by changing political strategies, a country may find the money for everything, for promoting industrial development, for mitigating climate change, for safeguarding the country from natural hazards. Indeed, it's not like that. I mean, of course, if we increase the efficiency of the economic and the political system, we can better spend the money. But at the end of the story, money needs to be found, and the way in a democracy to find money is through taxation. Then we can discuss how to apply taxation, whether or not taxation should be flat or proportional to the income. We can have several discussions, but at the end of the story, it's taxation to be paid by the citizens. So we have to be careful, because if we take wrong decisions, or if we take the right decision but we are excessively precautionary, then the impact on society, on the citizens, is potentially heavy. So we have to take into account these changes, but in a way that is technically correct and with an engineeristic approach, meaning that we have to find the best compromise in the face of uncertainty. Okay, now, here there are some guidelines, and some of these guidelines are already, I already mentioned. The effect of climate change vary by region. So we often talk about global climate change, but we have to consider that at the regional level there are differences. There is a big difference if you rely on snowmelt for water resources or not, for instance. And keep in mind that this requires a refined hydrological analysis. So we have to get a perception of what is the effect of variability and change in the given region. And the effect of climate change may vary across demographic groups, because, as I said, it depends on the composition of the society, on the wealth of society, etc. Climate change poses both risks and opportunities. This is something that is very often ignored. We assume that everything changes with respect to the natural situation is bad. Actually, very often the human intervention translates in an improvement of the quality of life, because this is what humans always try to do. The natural environment is very hostile, so we try to, for instance, to drain the lands, because we don't want marshes which are unhealthy, and we want to drain the land because of course we want to use the land for agricultural production. So the current environment, it's not natural, it's completely changed with respect to the original situation. If you look at this land here, originally it was a forest with marshes in the forest, and it was completely unhealthy, and therefore already the Turian started by draining and cutting the trees in order to get agricultural land to promote agriculture, of course. It's completely, I mean, the human intervention, in most of the cases, it's positive. It translates in an healthier environment, and an environment that is more accessible to humans. Of course, there are implications, and these implications we have to take into account, because otherwise the transformation can become unsustainable. There is to say that nature and humans are part of nature, have a inner resilience that is very, I mean, humans were able to resist to wars and global tensions that were very heavy already, and I mean, I think it's not a problem of collapse of the planet and collapse of humanity. It's a problem of finding the best way to develop in a sustainable manner. Adaptation comes at a cost. I already spoke about it. Adaptive responses vary in effectiveness as demonstrated by current efforts to cope with climate variability. And keep in mind that adaptive responses, again, have different responses, different efficiencies depending on the local situation. And here there is a list that I leave to you to read. Okay, now there are some solutions. Here there is a list of potential solutions, but keep in mind that the list of the solution comes in part from classical literature. Classical literature means that we already know that, for instance, if we connect water supply systems, we increase their resilience. Because if you have a drought in a water supply system in Bologna, and the supply system in Bologna is connected with the supply system of neighboring cities, you can share water. And therefore, you can benefit from different sources. Another solution, diversity of sources. It's not a good idea to have a water supply system that only relies on surface water. It's not a good idea to have a water supply system that only relies on groundwater. So if you have a diversity of sources, this is a classical solution. It's much better. So we already know from classical engineering that water supply systems should be oversized a little bit, and we have safety factors for that. We engineers are used with safety factors. And usually these safety factors have a value of 1.5, which means 50% more. We are used to that. And 50% more means, a lot of caution, a lot of prudence already. It means a very cautious approach. We know from classical literature, as I said, that we need diverse sources and we need to interconnect the systems. We know from the literature that pressure systems are more efficient than open flow systems. We already know that. So a possible solution for irrigation is not to use canals to deliver water, but pipes, pressured systems. This is a classical solution. We know from classical literature that in pressured systems we should keep the pressure low to minimize leakage. And we know from classical literature several solutions for minimizing leakage. I'm not talking about this because this is classic. So we have to benefit from the knowledge of these classical solutions. Some of them are listed here. And we have to devise, to think